In this video, I want to use NumPy to estimate the answer to this question of if I choose 3 random numbers between 0 and 2, what's the probability that z, the third of the 3 numbers, is strictly greater than x squared plus y squared? And so geometrically, here you can see that I've plotted the box from 0, 2, 0, 2, 0, 2. And then what I'm asking here is, what's the probability that z, if I choose it randomly within this cube, what's the probability that z is strictly bigger than x squared plus y squared? So that's like saying, what's the probability that it is above this paraboloid here? So I'm going to do this using NumPy. And let's see, let me make a code cell and import NumPy as NP. And then I need some way of making random simulations. So like in a previous video, I'm going to define RNG for random number generator equals np.random.default RNG. And in the previous video, we used RNG.integers to choose integer points. Here we want to choose real numbered points. So I'm going to do RNG.random. And if I'm not sure how it works, I can always surround it with this help. And then the most important things to notice are what sort of inputs does this take? Well, it's sort of weird that unlike integers, it does not take a high and a low because it's always going to choose between 0 and 1. So if I wanted to instead choose between 0 and 2, then I can multiply the whole thing by 2. So let me do RNG.random. Let me say size equals, and let me start with a small random array. Let me say 5 rows by 3 columns. Okay, 5 rows, 3 columns, uniformly distributed between 0 and 1. If I want it to be uniformly distributed between 0 and 2, like for this problem, then I should multiply it by 2. So I'll say 2 times. Okay, good. And let's save this with the name ARR for array. Okay, and this is the same type as the other NumPy arrays we looked at. Okay, in this case, it's 2-dimensional instead of 1-dimensional. So I think of it like a matrix instead of thinking of it like a vector. And so now within each of the rows of this, I want to ask, is this column strictly bigger than the square of this column plus the square of this column? So if I just want to get access to the 0th column here, I can do ARR square brackets and then colon. You should think of that as saying, give me every row. And then 0, you should think of that as saying, give me the 0th column. Okay, so notice how these numbers are the same as the numbers in this 0th column. And if I want to square it, so for example, 0.3 times 0.3 is 0.09, and here's that 0.09. Okay, good. So think of this as like the x squared, the squares of all the elements in the 0th column. And then I can do ARR colon 1 squared. Okay, so this is the squares of all of the elements in the first column, okay, where I start counting at 0, like usual in Python. And then here's the interesting thing. I want to know, true or false, is the number in the 3rd column, is that strictly bigger than the sum of these squares? So how can I do that? Well, I can say ARR colon 2, strictly bigger than the sums of these. And let's see what happens. So this says true in the top row, false in the next row, and so on. And then if I want to know how often was it true, well, the best way I know to do this is to use a built-in function to NumPy, which is called count non-zero. Okay, and so in this case, this should return the number 1 because there's exactly 1 true here. Okay, NumPy is thinking of true as like the number 1, and it's thinking of false as like the number 0. So that's why count non-zero is the same as counting how many trues show up here. This thing with the trues and falses, this is what's called a Boolean array. Okay, it's an array of trues and falses. So when I execute this cell, I expect it to say 1 as the answer. Okay, perfect. And let's see, I eventually want it to be a probability estimate. So I think of this as like, how many times was it successful? Like if my experiment is choose a point in here and then see, is it above or not? Then each time it is above, that's a success. Each time it's not above, that's a failure. And so I can do ARR, or let me do it slightly differently. I can do length of ARR. And this should tell me how many rows were there. In this case, there are 5 rows. So if I do this divided by length of ARR, okay, then this says 1 divided by 5. So my probability estimate here is 20%. So that's all good. Now, only thing I need to do is make the number much bigger than 5. So instead of 5, let's do 10 million. So 10 to the 7th. And I'm not going to print it out anymore, so maybe I'll delete some of these. But this, if I wrote it correctly, should work exactly the same. And this should be a much more accurate probability estimate than this 0.2 estimate. Let's see. Okay, so it's surprisingly close to 0.2. Let's try again. So let's try, instead of 10 million, let's try 50 million. And let's see, does it stay close to this 0.196 as I hopefully make it more accurate? So you can see it stays extremely close to this 0.196. So that is going to be our probability estimate. Yep, that's all I'll say in this video. Thank you for watching.